The first week of this module covered single linear regression. The single regression approach is used when you have one independent variable and one dependent variable. This chapter presents multiple linear regression too, which is used when you have two or more independent variables and one dependent variable. The research question for those using multiple concerns how the multiple independent variables, either by themselves or together, influence changes in the dependent variable. You can use the same basic concepts as the single linear regression, except that now you have multiple independent variables. The object of multiple linear regression is to develop a prediction equation that permits the estimation of the dependent variable based on the knowledge of one or more independent variables. After completion in this chapter, you will be able to accomplish the following items. Now I want to tell you a little bit about the research scenario we're using in this online lecture. We're going to be referring to task 7 in the Smart Alex examples that you have at the end of the chapter. And Caldwell, Pike, and Dunn investigated whether household chaos predicted children's problem behavior over and above parenting. From a sample of 118 families, the researchers used a number of instruments to record these variables in the SPSS file: the age of the younger sibling, the gender, the child's warmth and enjoyment relationship with his or her mother, their anger and hostility relationship with the mother's positive relationship with the child, the mother's negative relationship with the child, and household chaos. Using this data, we are going to do a hierarchical regression in 3 steps. So in Model 1, we'll look at child age and gender and the effect they may have on the outcome variable. Then Model 2, we're going to add these variables: the parent-child positivity, parent-child negativity, parent-child warmth, and then parent-child anger. Then for Model 3, we're going to add only one more variable, which is the household chaos. The research question we're going to address is household chaos predictive of child's problem behavior over and above parenting? So when we want to build a model with several predictors, we still have to consider the data assumptions, sample size, and the model fit as you would when running a single linear regression. It is important to remember that SPSS may appear to be very clever, but it's not. SPSS will happily generate any output based on any of the garbage you decide to feed it into. It will not judge you. It will not give you any indication of whether your model is valid or generalizable. SPSS will provide you the information necessary to assess things, but we have to rely on our own brains and understanding of statistics to evaluate the model. So in addition to the problem of selecting predictors, there's also several different ways in which the variables can be entered into a model. A great deal of care should be taken in selecting predictors for a model because the estimates of the regression coefficients depend upon the variables in the model. The predictors included and the way in which they're entered into the model can have a great impact. Do not select hundreds of random predictors and place them in a regression analysis and just hope for the best. You should select predictors based on a sound theoretical rationale or a well-conducted past research that has demonstrated the importance of those variables for the topic you're studying. Hierarchical regression predictors are selected based on past work, and then the researcher decides in which order to enter the predictors into the model. As a general rule, Known predictors from other research should be entered into the model first in order of their importance in predicting the outcome. Then after known variables have been entered, you, the researcher, can add any new predictors into the model. New predictors can be entered either in one go or in a stepwise manner or hierarchical. So, like hierarchical regression, you could do forced entry method, which relies on good theoretical reasons for including the chosen predictors. But unlike hierarchical regression, the researcher makes no decision about the order in which the variables are entered. All of the variables are entered at one time. And some researchers believe that this method is only appropriate when you are testing a theory. And then in stepwise regression, variables are entered into the model based on a mathematical criteria. And this is a very controversial approach, and it is not one that I recommend you use in most cases. Variable selection can depend upon only slight differences in the semi-partial correlations, and these slight numerical differences can lead to some major theoretical differences in interpretations of your data. So these models are often distorted by random sampling variation, and there's a real danger of overfitting your data. A final additional concern when we want to include more than one predictor in our model is multicollinearity, which exists when there is a strong correlation between two or more predictors. Perfect collinearity exists when at least one predictor is a perfect linear combination of the others. If there is perfect collinearity between predictors, it becomes impossible to obtain unique estimates of the regression coefficients because there are an infinite number of combinations of coefficients that would work equally well. Put simply, if we have two predictors that are perfectly correlated, then the values of B for each variable are interchangeable. Remember that B is for beta. The good news is that perfect collinearity is rare in real-life data. So as collinearity increases, so do the standard errors of the B coefficients. And if you think back to what the standard errors represent, then big standard errors for B coefficients mean these B's are more variable across their samples. Therefore, the B coefficient in our sample is less likely to represent the population. So crudely put, multicollinearity means that the B values are just less trustworthy. You have two or more independent variables that are highly correlated with each other. You would have trouble with the size of R. This leads to problems with understanding which independent variable contributes to the variance explained in the dependent variable, as well as technical issues in calculating a multiple regression model. If, however, the two predictors are completely uncorrelated, then the second predictor is likely to account for a different variance in the outcome than that accounted for the first predictor. So although in itself the second predictor might account for a little of the variance in the outcome, the variance it does account for will be different than that of the other predictor. So you have to have uncorrelated predictors. And multicollinearity between predictors makes it very difficult to assess the individual importance of a predictor. If the predictors are highly correlated and each accounts for the similar variance in the outcome, then you don't know which of the two variables is actually important in predicting your outcome. One way to identify multicollinearity is to scan the correlation matrix of the predictor variables and see if any correlate above 0.80 or 0.90. And as you can see in our data from our scenario, we have no correlations that are above 0.80 or 0.90. And remember, you only need to interpret the top half or the bottom half of the data since the values are going to be repeated. To check for multicollinearity, you can also use the variance inflation factor, or VIF, from the table labeled coefficients in the SPSS output. VIF will indicate whether predictors have strong linear relationships with other predictors, and then we can apply the guidelines from section 8.5.3 to our model to interpret it. So related to the VIF is the tolerance statistic, which is its reciprocal, which is 1 divided by the VIF. So although there are no hard and fast rules about what value of the VIF should cause concern, there are some general guidelines. The VIF values are all well below 10, and the tolerance statistics are all well above 0.2. So therefore, we can safely conclude with our data that there is no collinearity within our data. So if you take the average of the VIF values and it is not substantially greater than 1, then there's also no cause for concern. Your tolerance needs to be below 0.1, which indicates a serious problem, and tolerance below 0.2 indicates a potential problem, and your tolerance scores in this data set are all above 0.2, so there are no problems with multicollinearity. Now I'm going to demonstrate for you how to run the multiple regression in SPSS for the scenario we're using in this online lecture. We first need to go to Analyze, Regression, Linear. Then we're going to make sure that we select the Mom and Dad SDQ all items child 2 as our dependent variable. For the first block, or the first model, we have 2 variables. It is the age of the younger child and the gender of the younger child. Next, we're going to build model 2. Model 2, we have to include the age of the younger child and gender, but now we're going to add the new predictor variables. Those include the BPI, mum, anger, and hostility, the BPI, mum, warm, and enjoyment, the mum PC relationship that's positive, then the mum PC relationship that is negative. Next, we're going to build the third model. So we have to incorporate age and gender, and then the last 4 variables here with anger and hostility, and the warm and enjoyment, and the positive relationship and the negative relationship. And then we add our very last variable, which is the new one. It's the household chaos. So you'll see now that we have 1, 2, 3, 7 variables in model 3. Now the next step to do is to make sure that we include the correct statistics. So we are going to click on the statistics dialog box that is within the program right here. And then we have several things we have to click on. Not only do we need the estimates, we also need the confidence intervals. We need our model fit, the R-squared change, our descriptives, our part and partial correlations, our collinearity diagnostics, and then the Durbin-Watson test, and then our case-wise diagnostics. But we do change from 3 standard deviations to 2 standard deviations. Then click Continue. The next thing we need to be aware of would be our regression plots and what we need to include in all of our PP plots and our QQ plots. So we click on plots, And the most important thing is just making sure that you select the correct variable. So the items here. So you are going to pick the ZPRED, and ZPRED is the acronym for Standardized Predicted Values of the Dependent Variable based on the model. Then the values are standardized forms of the values predicted by the model. And then we're going to use the Z-resid, and that's just the standardized residuals or errors. And those values are also standardized differences between the observed data and then the values that the model predicts. And it's important to know where to place these two items. So the Z-resid here, you're going to move to Y. And then the Z-pred here, move to X. Then click on histogram, click on the normal probability plot, and click on produce all partial plots. And you'll see that it will do, for the model 2, you'll have to bring these over again. So I always make sure Z-res, Y, Z-pred here, and then the last one. And so we'll have to move the Z-resid to Y, the Z-pred to the X. Okay, so we click continue. And then if you'd like to save your linear regression, you can do so. It saves all your diagnostics, and those can just help you assess how well the model fits and the sample, and then how to help detect any cases that have some large influences on the model generated. And there's a number of items I'm going to have you click on. And if you want to know more about the details for each one of these items, your textbook provides a nice description for each. And then for the further options, you can click on that, and then you can make sure it knows that you want to use the F values, or if you want to use the probability of F. And I like using the probability of F. I also want to make sure I've included the constant in the equation, and I exclude any cases listwise. I click continue, and now all you need to do is click OK, and then you're going to get your data as the SPSS output, and I'm going to analyze the data for you by having each one of these tables presented in the PowerPoint presentation with further descriptions for you on how to interpret the information. Now that we have gathered the information we have for the SPS output, I'm going to walk through the different tables and explain how to understand the data that you can use to report your multiple regression summary tables. So one of the first things you'll notice is a descriptive statistics table. This table is not necessary for interpreting the regression model, but it is useful as a summary of your data. And in addition to the descriptive statistics table, selecting this option also produces a correlation matrix. And this table shows three things. First, it shows the value of the Pearson's correlation coefficient between every pair of variables in your different models. And remember that you use the descriptive statistics to check the correlation matrix for multicollinearity. That is, predictors that correlate too highly with each other, particularly R greater than 0.8 or 0.9. Second, the one-tailed significance of each correlation is displayed. And then finally, the number of cases contributing to each correlation is shown. The next section of your output will describe the overall model. So it tells us whether the model is successful in predicting whether a household chaos predicts younger siblings' problem behavior over and above maternal parenting. And remember that we chose a hierarchical method, and so each set of the summary statistics is repeated for each stage of your hierarchy. And an SPSS tells us what the dependent variable or outcome variable was and what the predictors were in each model with these small alphabetical letters. And then in the column labeled R, right here, are the values of the multiple correlation coefficient between the predictors and the outcome. And then the next column gives us the value of R squared, which we already know is a measure of how much of the variability in the outcome variable is accounted for by the predictors. And so for this data set, the first model has an R square of 0.006, which accounts for 0.6% of the younger sibling's problem behavior. However, when the other 4 variables are included in the model, the variance now increases to 0.065, and that is an increase to 6.5% of the child's variable behavior being explained by those variables. And then in the last model, household chaos was added to increase R squared to 0.11, or 11% of the variance in child problem behavior. Now, your change statistics are in these columns right here, and they're only provided if you're requested, and these tell us whether the change in R squared is significant. So the change is reported for each block of the hierarchy. So model 1 causes R squared to change from 0 to 0.006. And this change in the amount of variance explained gives rise to an F ratio of 0.273, which is not significant, with a probability of 0.762. In Model 2, in which 4 variables have been added as predictors, R squared increases by 0.060, making the R squared of the new model 0.065. This increase yields an F ratio of 1.42, which is not significant. And in Model 3, in which household chaos has been added as a predictor, R squared increases by 0.044, making the R squared of the model 0.11. Well, this increase yields an F ratio of 4.37, which is significant at a p-value of 0.04. So the change statistics therefore tell us about the difference made by adding new predictors to each of the models. The next part of our output contains an ANOVA that tests whether the model is significantly better at predicting the outcome than using the mean as a best guess. So specifically, the F ratio represents the ratio of the improvement in prediction that results from fitting the model relative to the inaccuracy that still exists in the model. And this table is again split into 3 sections, one for each model, and we're also told the degrees of freedom for each term, and if the improvement due to fitting the regression model is much greater than the inaccuracy within the model, then the value of F will be greater than 1, and SPSS calculates the exact probability of obtaining the value of F By chance, the ANOVA tells us whether that model is a significant fit of the data overall by looking for values less than 0.05 in your column named SIG. The next part of the output is concerned with the parameters of the model. The format of the table of coefficients will depend on the options you select. Now, the confidence interval for the b-values, collinearity diagnostics, and the part and partial correlations will be present only if selected in the dialog box. The first part of this table gives us estimates for the b-values, and these values indicate the individual contribution of each predictor to the model. And we're only going to use the b-values because they tell us the relationship between the child's problem behavior over and above parenting in each predictor. And so if the value is positive, we can tell there's a positive relationship between the predictor and the outcome, whereas a negative coefficient represents a negative relationship. And for the data of all the predictors in the third model, you'll notice that they have a positive b-value indicating positive relationships, and the b-values tell us to what degree each predictor actually affects the outcome if the effects of all the other predictors are held constant. So each of the beta values has an associated standard error indicating to what extent these values would vary across the different samples. And these standard errors are used to determine whether or not the b-value differs significantly from 0. A t-statistic can be derived that tests whether a b-value is significantly different from 0. It is easiest to conceptualize the t-tests as measures of whether the predictor is making a significant contribution to your model. Therefore, if the t-test associated with a b-value is significant, that's if the value in the column labeled SIG is less than 0.05, then the predictor is making a significant contribution to the model. So the smaller the value of SIG and the larger the value of t, the greater the contribution of the predictor. And from the magnitude of the t-statistic, we can see that the household chaos predictor variable has an impact. We're also given the confidence intervals for the betas, and the confidence intervals are accurate only if those assumptions discussed in Chapter 5 are met. So now we need to check the residuals for evidence of any bias, and we will do this in 2 different stages. The first is to examine the case-wise diagnostics, and the second is to check the assumptions discussed in Chapter 5. So SPSS produces a summary table of the residual statistics, and these should be examined for any extreme cases. And the output shows any cases that have a standardized residual that is less than 2 or greater than 2. And an ordinary sample would expect 95% of our cases to have standardized residuals with about plus or minus 2. And we have a sample of 118. So it's reasonable to expect 6 cases to have standardized residuals outside of those limits. In addition, 99% of our cases should lie within plus or minus 2.5. And so we would expect only 1% of our cases to lie outside these limits. And from the cases listed here, we have 9, 12, and 64. It is clear that 1 case lies outside of the limits, and therefore our sample appears to conform to what we would expect for a fairly accurate model. and case 64 has a standardized residual greater than 3. So it is large enough for us to investigate further. One way we'll do that is by now looking at the data editor for values of Cook's distance. None of these cases have a Cook's distance greater than 1, even case number 64. So none of these cases have an undue influence on the model. The average leverage can be calculated using the formula on the slide, and so we're looking for values either twice as large as 0.14 or 3 times as large, 0.21, depending on what statistician you cite, and all cases are within the boundary of 3 times the average, and only one case is close to 2 times the average, so this is really not going to impact our data. And then none of our cases come close to exceeding the criterion of 15 for a small sample size when we're looking at this Mahalanobis distance. However, Barnett and Lewis in 1978 is a good source of information to consult for more detailed analysis if needed, and the evidence does not suggest any major problems with influential cases within our data. Now we need to check for bias in our model, and that's particularly investigating the assumptions from Chapter 5. So we're going to look for evidence of bias. And I really urge you to review Chapter 5 to remind yourself of the main assumptions and the implications for violating them. So we're going to look at linearity, homoscedasticity, independence of errors, and normality. We can look for heteroscedasticity and nonlinearity using a plot of standardized residuals against standardized predicted values. If everything's okay, then the graph should look like a random array of dots, and if the dots create funnels, then that is a sign of heteroscedasticity, and any curve suggests nonlinearity. Note how the points are randomly and evenly dispersed throughout the plots on this slide. This pattern is indicative of a situation in which the assumptions of linearity and homoscedasticity have been met. If you requested the Durbin-Watson statistic, it would be found in the last column of your model summary table. And this statistic informs us about whether the assumption of the independent errors is tenable. And as a conservative rule, I suggest that values less than 1 or greater than 3 should definitely raise alarm bells. Although I do urge you to look up precise values for your situation of interest to make sure you interpret the data correctly. So the closer to 2 that the value is, the better. And for these data, the value is 2.024, which is close to 2, and that the assumption has almost certainly been met. And then to test the normality of residuals, we want to look at the histogram and normal probability plot, and the distribution is very normal. The histogram is symmetrical and approximately bell-shaped. The PP plot shows up deviations from normality as deviations from a diagonal line, and for our model, the dots lie almost exactly along the diagonal, which is a way to indicate normal distribution. So hence the plot also suggests that the residuals are normally distributed. Now, in the event that you violate an assumption, This problem can largely be overcome by using robust methods such as bootstrapping to generate confidence intervals and significant tests of the model parameters. But this chart can also help you know how to address heteroscedasticity, non-normality, and the lack of independence. Now that we have interpreted our output and we've checked that we've met all of our assumptions and that we have no issues with the residuals, we need to report our scenario's multiple regression results using APA style. Typically, when reporting the results of multiple regression analyses, two tables are used: a table of means, standard deviations, and correlations for your predictor and dependent variables, and a multiple regression analysis summary table. So for hierarchical regression, you should report these values at each stage of the hierarchy: the beta values, the standardized beta values, the standard errors, your R-square, and your adjusted R-square are also very helpful in your table. And if you do use a table, do not report the same information in the body of your text. APA does not say much about how to report regression results in the text, but if you would like to report the regression in the text of the results section of an abstract or journal or in your thesis, you should at least present your t-value, your degrees of freedom, the significance value, the beta value, and your R-square. So let's take a look at how it would look for your scenario in this online lecture. This is a table created in APA style that shows the descriptive statistics. And I noticed right here I have mean, standard deviations, and intercorrelations for the outcome and predictor variables. And you'll notice that this is my outcome variable. And then I have to list all of my predictor variables, and you would have your mean in this column, your standard deviation in this column, and then you would have the correlation coefficients for all of those items. And if there is a statistically significant correlation coefficient, you would want to make sure you have your p-values down here just below your table. Then you would have your regression summary. So the one I've chosen to write is the one on this slide. And I say that multiple regression analysis was used to test if household chaos significantly predicted children's problem behavior over and above parenting. Household chaos significantly predicted younger siblings' problem behavior over and above maternal parenting, child age, and gender. I have T in the parentheses, your degrees of freedom equals 2.09, comma, and then my p-value, which is exact because it is below 0.05. Then I'll state that the positive beta value indicates a positive relationship between household chaos and the younger child's problem behavior. The value of R squared, 0.11, for household chaos accounts for 11% of the variance in the child problem behavior. So that's my text write-up. Now what I'm going to do is make a reference to the regression summary table. So I could say something as seen in table 2 are the hierarchical regression analysis summary table. And in this table, because the slide is not very big, I've had to split the table into 2 slides. But it does show you what each step is, and then the beta, the standard error for beta, the standardized beta, the R squared, and then the adjusted R square. And you'll notice that the R-square and the adjusted R-square are only reported for each step, not each of the individual predictors. So for the standardized betas, there is no 0 before the decimal point because these values should not exceed 1. But for all the other variables less than 1, then that 0 is present. And the R-square for the initial model and the change in R-square, which is noted as that triangle R-squared, for each subsequent step of the model are reported in the table. And here's your continuations showing step 3. Now, if you have additional questions about multiple regression, you can find me through Canvas inbox or send me an email at kelsey.hall@usu.edu, and I look forward to answering any questions or clarifying any information for you. Thanks.